Good afternoon, everybody. My name is Maureen, and I just want to thank you for joining us for our web conference today, Basics of Biomedical Data Acquisition. Just to give you a quick overview, we're going to be covering during this session some PowerPoint slides in regards to biomedical data acquisition. We'll have a live demonstration, and then at the end will be a time for some questions and interactive discussion pertaining to the demonstration. I'd like to introduce you to Dr. Eric Peterson. He will be giving the presentation today. Eric is an electrical engineer here at Great Lakes Neurotechnologies, and he did his PhD at Case Western Reserve University in biomedical engineering. So with that, I'd like to hand it off to Eric.
Thanks, Maureen. So today's discussion will focus on data acquisition in biomedical systems. Switch this over. Continuous analog signal and digital signal. When done properly, the discrete digital signal will accurately represent the original signal that you measure. Biomedical signals arise from changes within biomedical systems, and because there can be so many different types of changes, from chemical reactions to ion transfer to muscle contractions, etc. There are a wide variety of potential biomedical signals to choose from for your application. Some common examples of biomedical signals include bioelectric signals, such as electromyogram, measuring EMG, measuring activity of muscles, electroneurogram, or ENG, which measures activity in nerves, electrooculography, sorry, it's a tongue twister, measuring the dipole moment of the eye to determine eye position, electroencephalography, which EEG, which is used to measure brain activity, and ECG, or electrocardiogram, which can be used to measure activity of the heart. But these biomedical signals can also include generated forces, positioning of the trunk, limbs, or head, respiration rates, volumes, etc., as well as blood oxygenation and throughout the body. So pretty much your imagination is the limit as far as the list of possible biomedical signals. The definition of what a typical biomedical signal is largely going to depend on its application. In, say, a metabolic study or experiment, you may measure cardiac activity with an ECG, muscle activity with EMG, and some sort of effort output such as force, speed, distance traveled, etc. Whereas in contrast, in a sleep study, you may be more interested in measuring brain activity with an EEG and respiration with a stretch sensor in order to determine sleep state. Both of these are applications where biomedical data acquisition is used to monitor the state of a system under different experimental conditions. In cases where an individual has volitional control over a biomedical signal, you may use this signal as a command source to interface with a computer or other device. One example would be using recorded EMG signals from skeletal muscles that somebody can flex and contract in order to control a device. We have a quick video example of that to show you here. Where the user here is actually controlling the robotic limb with his muscle contractions. So while the array of biomedical signals and applications are very broad, the process of data acquisition is still largely conserved across all of those different applications. We'll follow the process that we'll kind of step through today. One thing that we'll address at each stage is are the potential sources for common noise that can enter into your data acquisition process at each stage. Noise will be any signal that interferes with the ability to accurately measure your targeted signal. So beginning at the beginning, the transducer is your interface between the biomedical system and your data acquisition system. The transducer is responsible for converting energy caused by energy change happening in the body into an electrical signal. Examples of transducers include electrodes, force plates, stretch sensors, photodiodes, and are at least as varied as the number of biomedical signals that you can record. As far as noise reduction goes, this is the main stage where you're getting your signal. You want to make sure that you're getting the highest fidelity measurement of that signal as you can. And so one important means to do this is to choose the right transducer for your particular application. This will involve looking at the specifications of that transducer to make sure that it does cover your needs. Positioning of the transducer is also very important. For example, if you're going to use electrodes to measure surface EMG from a muscle in the forearm, you'd want to properly position the electrodes to help isolate the signal that they're getting from the muscle that you're targeting, as opposed to noise from nearby muscles, which you won't necessarily be able to identify as a different signal than the EMG that you're looking for. Finally, once the signal is transformed into an electrical signal, any time that it spends transferring from the transducer to the next stage in the amplifier, there's potential for electrical noise to couple onto the system. Typically, most commonly you'll see a 50 or 60 hertz noise that couples on. That's due to just the AC power lines within the building that you may be collecting data in. But other electronic sources can cause noise as well. By minimizing the distance between transducer and amplifier, you can help to minimize the opportunity for these noise sources to couple onto the signal. The amplifier is responsible for applying a multiplicative factor to your signal to amplify it or turn up the volume on it in the would be the analog for a audio signal. Typically, the transducer output isn't strong enough on its own in order to continue through the data acquisition process. So this amplifier will help to increase the signal strength and help make the signal more robust to noise that could be added along the way. There are 2 points to note as far as reducing noise in the amplification stage. First is whenever possible, if you can use a differential over a single-ended amplifying mode, this will help the rejection of common mode signal. So what this means is if you have 2 electrodes on the arm, and because of constraints of the of your biomedical system, you need to place the amplifier and the rest of the data acquisition device elsewhere. The wires connecting between the data acquisition device and the transducer will pick up noise, but because they're running along a similar path, should pick up similar noise. So if you use a differential amplifier, the common signal on the 2 of them will largely be rejected, whereas the difference in voltage between those 2 signals will be amplified. In a single-ended case, the amplifier just or applies the multiplicative factor to a single voltage coming in with reference to the ground. The other opportunity for noise to get in is in the actual amplifier circuitry itself. In critical applications, you want to make sure that you're using a low noise amplifier. Not all electronic components are equal in this respect, and there are many good low noise designs out there. The frequency filter is all about removing noise for your system. This provides the opportunity to set which frequencies are going to be allowed to pass along in your analog to digital, or in your data acquisition system. The there are two main features that this frequency filter can perform. The first is to attenuate unwanted frequencies. The signal coming in to your system is largely going to be comprised of many different frequencies, and several of these are probably necessary to describing the system that you're trying to measure. However, some are probably going to be noise frequencies that enter in as well. So the frequency filter allows you to attenuate certain frequencies. The example shown in the diagram is a low frequency signal with high frequency noise coupled onto it. By passing the signal through a low pass filter, we can effectively block the high frequency signals and only allow the low frequency through and decouple that noise from the signal. If instead, in our example, the signal we wanted was the high frequency signal and the noise was the low frequency signal, we would apply a high pass filter that would only allow the high frequency signal through and help block that low frequency signal. The other important aspect that the frequency filter has is it has to perform some amount of low pass filtering, which sets an upper limit of the frequencies that are allowed to pass into the next stage, the analog to digital conversion. Without this upper limit placed on the frequencies that continue on to the next stage, you can get much higher frequencies looking like low frequency signals in your output data, which would impact that accuracy. We'll talk a little bit more about how this can happen in a couple of slides. Before going in depth with the analog to digital conversion, I want to just cover why we even deal with this stage, kind of the motivation behind it. We're taking this analog data, sampling it at a certain rate, taking snapshots essentially of that, and using that as our digital representation. If we know the sampling rate that we took those snapshots at and those values, we can reconstruct the original signal depending on how it was collected. Digitized data is nice because it can be easily stored and copied and opens up the possibility of using powerful computing tools to do repeatable and potentially automated analysis. This stage is also important to select low noise electronics so that the analog to digital conversion doesn't, so you can minimize the amount of noise that this stage does introduce to the system. I mentioned before that it's important that the frequency coming into your analog to digital converter is limited to a certain level. This is illustrated in these 5 diagrams where we see the original signal in black and the digitized signal that is a result of sampling at different rates in blue. The little red dots are the samples that would be taken at each time point. What we can see, looking at the different sample frequencies, when the sample frequency is equal to the signal frequency, we get a representation of the signal that looks like a flat DC signal, when in reality the signal is alternating and changing considerably. In this case, we would get very inaccurate measurement of what we're trying to, what we're actually trying to represent. If the sample frequency is doubled to twice the signal frequency, we get maybe some more data out of the digital representation. However, it's very distorted and is going to depend on how we align to the input signal, which we can't know a priori because we haven't measured the signal yet. Therefore, there is a rule or sampling criteria that was outlined by Nyquist, saying that your minimum sampling frequency must be at least twice the signal frequency. So we see in the other three diagrams, as we increase the frequency, we get a higher and higher resolution or higher and higher fidelity representation of the original signal in our digitized signal. The cost of this is, at this increased sampling frequency, is the need for higher speed electronics, as well as because this digitization is generating data, we're generating more and more data for each increased sample frequency. So in cases where you're recording many, many channels or are transmitting the data wirelessly, you may be limited by the bandwidth of your system, limiting your ability to transmit data to your hard drive or wherever. So that's something to note. In a case where you may need very high fidelity in your signal, such as analyzing and comparing differences in the QRS complex of an electrocardiogram, you would want to make sure that your system can handle very high frequency, sampling frequency, so that you get a very high fidelity signal. Whereas in the case of using EMG for a motor control or computer control device, or application, where typically the signal is rectified and integrated anyway, we're not so interested in the exact fidelity of that EMG signal so much as detecting the presence of it and magnitude of it, in which case sampling at a lower frequency will allow us to do so on perhaps more channels or open up the possibility of wireless transmission. The other important parameter to note in your analog to digital conversion is the resolution. This will set the this sets the number of discrete voltage levels that can be digitized in your system. Excuse me. Basically setting the smallest detectable difference between two sample points. Increasing resolution will increase the fidelity of your signal, but only up to a point. If your resolution increases beyond the level of your noise in the system, you'll be resolving noise and you'll be using extra bits of data that won't actually be giving you real information and just be noise. Resolution does come at, increased resolution does come at a higher computation cost as well because you are generating more data. However, your resolution increases by a factor of 2 for each bit of resolution added. So 13-bit resolution A to D is twice the resolution of a 12-bit A to D. Once you have your signal digitized, you can now use computational resources to help post-process or analyze your data. This can include statistics such as means, standard deviations, etc. But it can also allow you to use powerful digital filters that can be configured quickly and reconfigured and applied to your data to analyze your data and understand what's going on. The example on the right I show on the top trace is a raw EEG signal. If we filter that same signal in several different frequency bands, we can start to see how different parts of the brain are active in different ways. And this is all coming from the one single copy that we have. We've applied 5 different filters to this one signal in order to look at these 5 different bands. If we were to do this on the analog side, after the amplifier, we'd have to build 5 separate frequency filters and do 5 separate analog to digital conversions, whereas in the digital realm, we can quickly reconfigure these filters and make new copies of the data filtered in different ways, all while preserving the original copy of the data, which is very powerful. Other post-processing techniques that are oftentimes used include the fast Fourier transform, which plots the magnitude of the frequency content of your signal. On the x-axis is frequency in the plot on the left, and the y-axis is the magnitude at that frequency. So by looking at the FFT of a signal, you can quickly see that this particular signal has a strong DC or 0 hertz component, but also has peaks at around 1, 6, and maybe 13 hertz as well. We can also see that most of the signal is contained in frequencies below 40 hertz. And this can be done, this is information that may not be immediately obvious by looking at the signal plotted in time as we had it plotted in the previous example or slide. The FFT looks at frequency content of the entire signal, though. If we wanted to track frequency content as it changes with time, then we'd use a spectrogram shown on the right. The spectrogram's axes on the x-axis is time, and the y-axis is frequency. And the magnitude at each time and frequency point is then plotted using the color scale. From this plot, we can see that as time progresses, the frequency content goes from typically very low, and we start to see an increase in higher frequency content of the signal. This may be, in the case of measuring EEG over premotor or motor cortex, may indicate somebody is planning or initiating a movement of their hand or whatever. And so you could combine this type of analysis with other biomedical signal inputs to start to understand how the system is working. So based on your knowledge now of data acquisition and biomedical systems, we're going to show you a quick demonstration and then open it up to questions.
Okay, thanks, Eric. I'm actually going to now show a device that we manufacture here at Great Lakes Neurotechnologies called the BioRadio. This is the BioRadio right here. It's a wireless 8-channel programmable monitor. And kind of going back to something that Eric mentioned earlier in the presentation, the 8 channels that you can see here on the front are differential inputs, all referenced to one ground. And you can program different parameters on each one of those channels to be appropriate for measuring different physiological signals. And I'll show that in more detail in a minute. The device uses a Bluetooth radio to communicate with a USB receiver and transmits that data over a range of about 100 to 150 feet. So Eric, if you want to take a second and kind of relate this back to some of the things that you were talking about.
Certainly. So the BioRadio here, this is going to contain the amplification stage that we talked about, the filtering stage, and the analog to digital conversion stage, and then it takes that digital information and then wirelessly transmits it. So the amplification stage has a configurable gain, which we'll talk about in a moment. The frequency filtering happens automatically based on your sampling rate that you set under your analog to digital conversion. So the Nyquist criterion is actually enforced for you in this device.
Okay. So now I'll actually, sorry, 1 second, open up the software application that we use with the BioRadio so I can demonstrate actually recording a true physiological signal. So like we just mentioned, the channels on the BioRadio are configurable across a few different parameters. The first thing that you can do is set your sampling frequency to be appropriate for the signal that you're measuring. And in this case, I'm actually going to be demonstrating an EMG signal, so I'm going to leave the sampling frequency at 960 hertz. You can also program your resolution. And the last function is you can set the input range of each one of these channels per the signal that you're recording. And from this drop-down, you can select the range that you need to use, which can be from the microvolt level for smaller signals like EEG, and all the way up to the volt level. So, Eric, how does this correlate back to kind of amplification of different physiological signals?
Yeah, so like I mentioned, the amplification is set in here. Ultimately, you can't set your amplifier gain higher than a certain range based on the voltages you have available. If you're trying to measure a 1 volt signal and you have a gain of 100, you're going to need 100 volts of swing in your amplifier to actually represent that signal. This is kind of computing that under the hood for you. It gives you're allowed to select the range that you have for your input signal, and then the gain is automatically set to give you the maximum gain for that range while still maintaining high fidelity data collection.
Great, thanks. So what I'm going to do now is program the BioRadio for recording one channel of EMG. I've selected an input range of plus or minus 6 millivolts and click Program Device here at the bottom. So now what it's doing is it's sending out all of those parameters to the BioRadio, and now we're ready to start data acquisition. So the one component that Eric mentioned about biomedical data acquisition is the transducer, or the interface between the body and your data acquisition unit. So for EMG, we use standard surface adhesive electrodes just like these, and then those connect to snap electrode leads, flop around, there we go, which then connect to the electrodes on the body. And the other end are no-touch connectors, and these are what plug into the differential inputs on the BioRadio itself. So I currently have, there we go, if you can see them, 2 electrodes placed over my wrist flexor muscle, and 2 electrodes because EMG is a differential signal. So I'm going to hook those up there. And then I'm placing my ground or reference electrode on the elbow here, since you do want to place that over a bony surface. So then the other end of the cable here will get plugged into the BioRadio, as I mentioned. So differential electrodes go into channel 1, and then the ground gets plugged into the ground input here. And I'll go ahead and click Start to begin data acquisition. So you can see that as I flex my arm here, you do get that increase in amplitude. And what I'll do first actually is just change the y-axis scale of this to get a little bit better picture of the EMG. There we go. So one of the things that you might see that's occurring is as I move these electrode leads around, the signal's getting somewhat distorted. And Eric had kind of talked thoroughly about different sources of noise. So what's something that we could do in this instance?
So in this case, the EMG is a high frequency signal, and the movement artifact is going to be a much lower frequency signal. EMG signal range, frequency range is in the hundreds of hertz, whereas these wires are moving around much slower than that. So we could set a lower limit of frequencies that we're going to digitize in this system using a high-pass filter set with a cutoff frequency of...
I'm going to set it at 30.
Okay. So this will help to reduce any frequencies below 30 while maintaining those above.
So exactly, so what you can see here is that you're still getting the high frequency EMG signal, but then as I move the electrode leads around, you're not getting that artifact or that motion artifact that's affecting the signal. So this is a really great thing to be able to use for something like an exercise physiology application where the subject might be moving pretty actively during data acquisition. Another thing I'll note is that there are different sources of noise that can affect signals like 60 hertz noise, which Eric mentioned, electrical noise. We do have low-pass filters, band-pass, band-stop. All of those can be applied to the signal to process it in the way that you need pertinent to your application. And then one other function in BioCapture that I'll show you is that you can actually do a real-time frequency analysis of the EMG signal. So again, you can take a look at that as I flex. And Eric had talked about, looking at the frequency analysis and the frequency components of the signal in comparison with the signal amplitude over time. So just another view that we have of the signal that you can take a look at. So I just wanted to provide a pretty basic demonstration of EMG data acquisition. With our software, you have a couple different options as to what you can do for the post-processing aspect of your data. The first is you can save data files here in BioCapture, export them to CSV for import into MATLAB, LabVIEW, third-party packages for your own custom analysis. And then another option you have is using some automated analysis packages that we offer. So I'm going to go ahead and stop this here. And what I'd like to do now is open up the floor to any questions regarding the presentation, regarding the BioRadio, anything that you might want to know some more information about. So if you'll excuse me, I'm going to jump over here. If you have questions, please go ahead and type them into the questions box on the GoToWebinar toolbar, and then we'll get to all of them in order here. Okay. Oh, good. So this is actually a great question. If I have my own sensors, can I use the BioRadio to record them or record with them, or do I just have to use your sensors?
No. So I think we can both kind of field this one. The data acquisition system that you use, if it can accept an electrical signal in certain ranges, then if your sensor is outputting this an electrical signal in those ranges, shouldn't matter. Again, you want to make sure that the frequency content of that signal is low enough that it's not going to be significantly distorted by the filtering stages that happen before the analog to digital conversion. So provided you're in the right ranges and you're looking for the right frequencies, should be no problem.
The input range on the channels of the BioRadio is plus or minus 2 volts. So as long as you have an output that's within our input range and having the appropriate interface in order to connect into the channels of the BioRadio, we have a lot of customers who integrate their own custom transducers pretty frequently. So okay, here's another question. What kind of radio is in the device and how does that fit into the block diagram that you showed?
Okay, so the radio is actually Bluetooth, which is nice because Bluetooth protocol is designed to be low power as well as play nice with or coexist with other devices operating in that same frequency band. So Bluetooth, Wi-Fi, some of the other wireless technologies are going to all operate in the same band. So Bluetooth is one that plays well with others. Where it fits as far as the block diagram, it would actually be more of a post-processing. It kind of fit right between the analog to digital conversion and the post-processing blocks. Because that post-processing is really happening on the PC, but the analog to digital conversion is happening inside the device. So once you've done the analog to digital conversion, you're not worried about noise on your data because it's been digitized. When packets are sent or resent, you're not going to get a change in that in what that data actually is. So I guess it's the little arrow between the A to the ABC block to the post-processing block.
Okay. Let's see, here's another question. So you demonstrated EMG data acquisition, but the BioRadio samples at a maximum of 960 hertz. If EMG occurs typically between 0 and 500 hertz, is some of the signal being lost per Nyquist? And if so, how does the BioRadio accommodate for that?
Certainly. So the BioRadio is going to accommodate for the frequencies that are allowed to pass to the analog to digital converter for you based on your sampling frequency. So it's not going to alias your signal and incorrectly sample something that's higher frequency than the sampling rate will allow for. However, that does mean that the filtering is going to filter out higher frequency components of that signal. Now, in many cases, the EMG signal is not something that you're trying to accurately measure every peak and trough in order to compare to something else. In that case, a more gross digitization of that signal is more than acceptable, especially if you're rectifying and integrating the signal for, which is commonly done with a lot of EMG data collection. So there will be some loss in the signal just because the filter is enforcing that, limit. But again, most of the signal is going to occur in the band that is being measured and digitized. So it should still work just fine, as you saw in the demonstration.
Okay. What is a good environment to record fatigue along with an EEG signal?
Okay. I guess depending on the type of fatigue, if that's something that you need somebody out moving around and it's that type of fatigue, a wireless unit would actually be very nice for that because you could have the individual actually moving around. If instead you are measuring the brain activity to find out if somebody is just mentally tired, that is going to be beyond me. I'm not exactly sure which brain region is going to give that best, and if that's going to be something that you can measure from the cortex. As most of the surface EEG signals are going to originate from the cortex, that'll be the main activity that you're sensing with that. So it would depend on the region of the cortex that actually is responsible for that. I don't know which one that is, though.
The one thing that I can add to that is with the BioRadio, we use individual gold cup electrode leads for recording EEG. So those can be individually placed on different regions of the brain or on the head, depending on the type of signal that you're trying to acquire. So whether it's in the frontal region, whether it's in the cortex, wherever it might be, you can place those to be appropriate for the specific signal that you're recording. And another example is we have several customers in psychology who like to record fatigue and correlate that with other types of physiological parameters such as ECG or respiration. Most of that's done in a lab if you're talking about a physical environment, but you can definitely record those types of signals with the BioRadio. So excuse me, let me check the next question here. Is there an application that allows data to be displayed in an Excel file?
Yeah, so you can output, you have to correct me if I'm wrong, but this data can be output into a CSV file, correct?
That's correct.
Where you'll get the timestamp and the recorded, the voltage recorded at each one of those timestamps. A CSV file, it plays well with Excel. So you have a list with a column of time and each signal's data. You can then use that to plot your time, your signal versus time, and do other some of the statistical analyses that we talked about. Excel would be perfect for doing some of that post-processing analysis.
Okay, we go to the next question here. Let's see. Does your company only teach people about these types of technologies, or is this something that you actually offer to sell? If you want, I can grab that one. So the webinar series here that we're offering really is, it's an educational component that we want to provide to our customers as well as to anybody else who's interested in different fields about biomedical data acquisition, physiological monitoring. The BioRadio is a tool that we sell and manufacture here, and it's used in a lot of different applications, biomedical engineering, physiology, psychology, for teaching and both for research. So if anybody wanted additional information about that, I'd be happy to follow up with you via email after the web conference to answer some direct questions.
And really, I mean, this is something we're passionate about. We enjoy teaching people about it. At least that's why I'm doing this. So yeah, that's part of it is something we get out of it too. It's just getting to teach people about biomedical signal acquisition and put those tools in your hands so that you can go out and do cool things with it.
Okay. Okay, I think that's it for our questions this afternoon. I just want to let you all know that I'll follow up with an email after the session here, and then if there are any further questions, feel free to get in touch with me directly. I'd like to thank you all for your time and thank Eric for presenting here for us today. And I hope you have a really nice rest of the day.
Thanks.